So now Hantao is recording, and what I'm displaying right now is the prep work. So just to make sure everybody has gone through these slides that you have there. So everybody has it installed. Show of hands.
What?
Show of hands.
Who installed or who didn't install?
Who didn't install? You.
No, I haven't.
Okay. Who did not install it? That's easier. Just you? Do you have the drive? Or? Okay, so I'm gonna these first slides that you have being displayed here is for setting up the system, right? So it's not that I'm not gonna really go into it in detail because it's meant for you to just have an aid and checking. Sometimes it's presentation view. What is this? Horrible. All right. So I will have two sets of slides at the same time. Sorry. Yeah. I will have two screens at the same time. On this screen here, we'll have the slide with the instructions of what we're doing on your left. And on the screen, I will be doing what the slide says. Okay? Right now, there's no example about this, but so, yep. The part one is setting up OpenModelica and setting up OpenIPSL. So setting up OpenModelica. I don't know the Mac users if you are using 9.6. You can't see the green, yeah, in this thing. So 9.6 is the one that I have tested. I haven't tested 9.11. Okay. I haven't checked it for other things. Then if you have Linux is way easier with Ubuntu because there is a direct download also through the repository. And if you need a virtual machine, there is some pre-configured virtual machines. I haven't tested that, but those are the options available already from the OpenModelica website. So OM-Edit is one way of interacting with OpenModelica. I will explain you the rest, but here we're just testing that you can run a solver, you can run a model. So this window is the main window of OM-Edit, which is the connection editor. And you're supposed to go to this one, select a solver, and run. And then when you're done running, this should say 100%. Ah, okay. This should say 100%. And then you can click on plotting. And then you can select on the plotting the speed of the phalange. And you should get something like that. So if you have something like that, everybody has something like that, except the guy that's installing it, so that's okay. Okay, that's the dog, so you know we're in OpenIPSL. I didn't have time to update the materials from the last tutorial, but the good news is that everything should be working because when I update it, but I'll put I will make something similar on GitHub and upload it with the logo of current, and then you will know you have the slides from today, because I always change something here and there on the slides. Just if it's good when I get feedback, but anyway, you should get the source here, and that's it. That's the latest version, so you get that source, everything should work. Then when you either drag and drop, and sometimes, depending on which version of OpenModelica you installed, that might not work. So then if drag and drop doesn't work, you go and do it, click on File, Load Library, and you open the folder where it is, and the dog should show up there, the Frenchie. And then, as I explained during the talk, the interesting things are the application examples that are like standard networks or some real networks. And that is under application example, so you should test that. And then you should click on the icon to simulate, which is that S, choose a solver, and you should indeed get something that looks like it's weird. So if you want to know why is the case, then we do what it's coming next, okay? So now I need to change to the next slide set.
Next,
Yeah. Anybody watches that show? Yeah, let's get thrifty. Okay. So if you have any friend that didn't come and wants to do this stuff, tell them to do this first, because sometimes the problems happen during installation. So at least many times it has happened to me. So that's why we have those. All right, let's take this away. Now, you should also have these hands-on slides. Now, the ones that say hands-on, OpenIPSL, and in the file name also, these are the ones that we're going to follow, okay? So, did you get OpenModelica installed? I already answered. You already told me, and you have the installer in the drive. If you haven't gotten it, etc. Right? Now, okay. So, what is it that we are? What is the goal today? The goal is that you get a brief introduction of OpenIPSL and some of its how you can use it to do power system simulation. That you learn how to use OpenModelica, at least one of the ways of using OpenModelica. That you implement a basic power system model. I don't know, how many of you have taken power system analysis at least?
Everyone.
So you learn transient stability stuff? So, okay, so it's basically a single machine infinite bus that we're going to build from scratch. And then we should analyze it with OpenModelica with different methods to do that. There's different ways. But most likely we will only do one, because I've never done this tutorial in one shot. People sometimes get trouble with the computer and so on, but don't be disencouraged. So if we can complete one of the examples using OMEdit, which is the basic interface, and then if we can do linear analysis using OM Notebook. So one thing that is very common in power system tools is that you only get the nonlinear simulation. You don't get the linearized model. With Modelica tools, you can get the linearized model for free. And that's very powerful, because now you don't have to use two different softwares or re-implement all the equations. You just define yourself the inputs and outputs. So if you want an internal state that is not measured, you just pick it up and define that that's what you need to do. In the course that I will be offering next semester, I will teach how to actually do that for, not for power systems only, but for different types of systems, mechanical and thermal, and maybe something else if I have time to prepare it. All right, so let's double check. I guess it's not necessary, but you should drag and drop, and you should have the little dog there. And then you should go to Applications, Examples, /tutorial, and then Tutorial folder. Inside of the tutorial folder, you'll see something called package. This is very common in Modelica libraries, that the name of the library is package, because what the package is doing is listing all of the files that are included in the library. That is so that you can manage the library with these source version control systems. Anybody has used source version control? One, learn source version control is the best thing you can do in your life. I didn't learn until the last year of my PhD, and I really regret it, because you make one change, you don't remember at 9 and then you're at 5, it's like, oh, something worked in the morning and now it doesn't. Source version control solves that, you know. So I really recommend it that you learn it. Okay, let's do this. OpenModelica. OpenModelica is actually not one piece of software, it's an environment, okay? At the heart of the environment, you have the OpenModelica compiler, or OMC. It's an interactive compiler. So there are many ways to interact with the compiler. We will use OMEdit. So basically, OMEdit is a graphical interface that allows you to do editing of the model, and when you save and you go and configure simulation, OMEdit sends the command of how to simulate and which model to OMC compiler, and then automatically retrieves the results. So this, all of the ways of interacting, you can think about as a client-server architecture. Basically, you send the request to the server, and then you get the results. OM Notebook, if anybody has used Mathematica, so OM Notebook is like a Mathematica environment. It's an interactive notebook. It's similar in a way to Juniper. If you have used Python and Juniper, it's kind of like that, but more limited because it's just for OpenModelica. And finally, we have the OM shell. We will not use OM shell, but in the appendix of the slides, you have how to linearize the model using the shell and how to do something else. I don't remember the simulation, I think. Learning command line is the best thing, the second best thing you can do after Git. Git is still the first thing. All right, so OpenIPSL is divided in different categories or sub-packages. So you find the models in application examples. They are all using OpenIPSL and a model from its sub-packages. The electrical has power system components, generators, lines, shunts, loads, and so on. Non-electrical is mathematical functions that are used so that you can actually get the same behavior as the power system tools. So one very interesting thing is that for some reason, the integrators are not having the same behavior in different tools. And that the reason is implementation. So just playing first, sorry, I skipped it. Modelica, the language specification, comes together with the Modelica standard library. The Modelica standard library is a library of functions that have to be supported by the Modelica tools. So all of the Modelica tools come with the Modelica standard library. And that Modelica standard library has a lot of different domains and blocks that you can utilize. So for example, under blocks, you can see functions for discrete and for continuous time. So under continuous time, you can find things, for example, the integrator.
Sorry, the slide is not, projector is not changing.
You know, it's because it's in this silly presentation view. I don't know why we use presentation view. Okay, I guess some people find it useful. All right, so here we go. Now you can see my desktop, right? Right, so let's go back. So open here a little bit bigger. Sorry, I have to use my mouse. That's why I need to sit down, so sorry about that. Where is the mouse? Here. Where is the mouse? Come on. Go. There we go. Come on. All right, when my mouse wakes up, you see here, this is the standard library. And then we go into continuous and you see the integrator. Now you have different views, as I was explaining. You have the icon view. It's just a picture that looks pretty. you have the graphical object view, or I think this is a diagram. So icon, diagram, and text view. So you don't need to open another file. This is exactly a model that you have. And if you look here, you have the equation of the integrator, which is derivative of y equal to k times u. That's it. Now, if you go, this is a different tool. It's called the Imola. It's a proprietary tool, so you have to pay a license for it and so on. But I just want to show you. My mouse is dead.
It's also Modelica.
Yeah. Oh. No problem. Go ahead. So yeah, you can also use, where is it? System Modeler. So I'll open it up, and you can use MapleSim. I also have it here. But my poor computer is already 96% RAM, so I'm gonna stop with this. But the fidget spinner that I was showing you, that I did it here because I have it. But you can do it in all of the environments. It was done by Johan Rodin. It's just a guy that is very into the Modelica. But what I wanted to show you is that here you have the Modelica the same Modelica standard library, right? So when you're implementing something and you need a special function, look if it's in the Modelica standard library, because that means that you're using something that has been tested to run in different environments, in different tools, and you don't have to maintain it. Somebody else has to maintain it, okay? So here you have the same, you see? And if you want the fidget spinner, I can put you in touch with, I just want to show you, it's so cool. So actually this just to change a little bit the topic, if it opens, this is a multi-body example, I think. Let's see if it opens, yeah. So here you have a phalange, and this is the edge of the spinner. So you're basically rotating it, and you're getting the damping out of it. And all the tools have animation features included. So this is actually what you were looking at, is the simulation being animated, and that comes included in the tools. OpenModelica can also do this 3D animations, but I haven't used it so much. In OpenIPSL, we use it for like the IEEE 9 bus model. You can look at the values of the flows on the lines. That's the only visualization we've done, because you don't really need to do much more than that. Let's see. So you see that in System Modeler, you actually have two windows completely separate, one for the modeling and one for simulation. So from System Modeler, you actually have to open another environment to run the model, which can be very convenient, but maybe it's for your 95% memory, it's not the best idea to do that, right? Anyway, so let's see, fidget, and then suggest variable. Well, maybe this is easier, phalange, and then you have derivative of angle is speed. It's speeding down, right? The speed goes down, and then if you go to animation, and then you move the view. So you see, you can correlate the physical behavior with the plotting one. Okay, and you can do this for any model, because all of the icon display, the diagram display, and the 3D is also in the standard. So you can actually guarantee that your visualization will work in all of the tools, which I think it's a great advantage. Anyway, so you gotta look at a couple of other tools, and the principle is the same. You have the library, and you can reuse the models everywhere, basically, okay? All right, so let me minimize this stuff and go back to the slides. All right, so in electrical, you have all the power system components. I'm going to do like this because this will avoid going into presentation mode and getting it slow all the time. All right, so then in interfaces, you have coupling blocks for sources and sinks, okay? You need to couple the stuff. How do you think we're going to couple electrical quantities? What is it? Huh? Any guess? Yeah, it's an equation, but which variables will you have in an equation? What is current or power? So no, you don't need to do power. Power is more complicated, but you can do power. But so what is a current?
Rate of change of charge.
Rate of change means there is a flow, right? Of electrical charge, so you have a flow. And what is voltage? Is it
Pressure sort of that pushes the charge.
okay? Potential energy, right?
Yeah.
Okay. So if you look at the interface block in OpenModelica, you will see here under interfaces, you have something called PW pin. So the pin is a node, like in Kirchhoff current equations, and the voltage is divided into real and imaginary part, and is defined as a real variable. Okay, that's a potential. But and just like when you're measuring voltage, you don't need to interfere with the circuit. In the model is the same thing. You can interface the voltage potential. But when the current is a flow, so that's defined as a flow variable. And this is the only thing that is kind of relevant for us, but people working with thermodynamics, they have a lot of flow equations. So for them, the flow is a very useful construct to use. We only use it for the current, really. Because in our other parts of the system, basically we have a control system that has an already defined direction. But the flow, as I was explaining this morning, you don't define the current flow in the model until you're simulating it. So it has to be able to decide how it goes. Okay, so that's the most important interface. And the other interface is an interface called generator. And this is actually a template. It's a template that will allow you to drag and drop to form a source. And you can use the same template for a load. Like inside of a load, you will have a tap changer controller, the load, and something else, and you want to put them all into the same block and have only one pin interface. You can use it with this template. So this we did it out of need, and you will see how we use this in the tutorial to build up a whole plant. So we just call it generator because we're used to saying that in power systems. So it makes it kind of easy and obvious for us. All right, and then you have types. These types are kilovolts and megavolt amperes defined in our library. The examples, as I said, they are not really examples, like illustrative examples or class examples. They are meant for doing unit tested of a specific component. So it's no wonder, and this is a bad name, just we didn't know how to do it correctly at the beginning. But if you go into machine, PSSC, you will see each of the generators having one example, because basically we use these models to test if we're getting the same result as PSSC. And we have left them there in case somebody else wants to double check what we're doing. So that's the main reason I'm having open source things, is because I'm tired of people questioning me that my stuff doesn't work. So I tell them, if you're smart enough, you can do it yourself and say that I'm wrong. So everything is there. So engineers are full of emotions. We should be full of technical arguments. All right, so there we go. That's the first slide. So make sure that you're playing around and getting familiar, so that then when we have to drag and drop, you do it. Electrical has all this stuff. Electrical machines, transmission lines, turbine, plus governors in the same thing. A turbine governor doesn't exist. You have a governor and you have a turbine. But in power systems, we have put them together in the same block. Don't get confused. They're different things. So you can see, for example, under controls, you will find the excitation systems. Under wind, you will find this example here, and so on. You see, we don't have HVDC because my student developed it and we have never integrated into the library because we were not using Git. And he has two of an old version to make it work now. So if anybody wants to help cleaning up that model and putting it back in, I'll give it to you. Now, here is these electrical blocks that are transfer functions, logical operators. More importantly, here you have saturation blocks. So, for example, in PSSC, the generator has a very specific saturation function. That's what we implemented there. You also have these integrators with limiters, ramp tracking, and so on. These are all necessary only because we want to get the same result as the standard tools. Otherwise, you don't need this. Use the ones from the MSL. These are just so that you get the same answer. Okay, this one I talked about already. All right, so let's go to the tutorial folder that you should have now in the computer. For me, it's automatically opened. So what happened with the, now I need that.
Yeah, it goes to sleep.
Yeah, that's fine. All right, so now we are gonna use more these two sides because now I'm gonna have to show you my computer on this side and the other thing on the other side. So let me see, I will blow it up here. All right, too bad my mouse died. All right, I'll do it by hand. So you see, when you load the library, when you drag and drop it, you have the dog, and when you drag and drop the tutorial, you will have this icon with like a play or play button. Yes, that's what we have in the slide also, and you see example 1. So that's the solution. Okay. So you don't really need to sit down here unless you want to. But the point is that you arrive to this step. Okay, so the ones that have the play button, those you can run. And this is valid in general in any Modelica library. The ones that have the play button, you can run. Now, inside of the solution is a step-by-step series of examples. So here, I'm taking you step by step from the slides. There is a solution for each step, okay? Now, we are going to work under the folder called Working Examples. Or, if you want to, you just go and create a new package. So you can go and say, new Modelica class, and say here, package. And you can say my package. All right. And that's the only thing you need to do. You can put it somewhere else, but I think that's fine. So now you have my package here. And that my package, you can do the same as we're doing under the working examples. Okay. So working examples, which is just a folder to put what you're doing, right? So the first thing that I do here is that I create a new Modelica class, and then I go and I say example 1, and that's gonna be a package also, and it's gonna be inserted into the class or package, my package. So that's actually the first step. And you can do that under working directories, but I think this is easier actually to have it in a different one. So I'll try while I'm doing it here. All right, so on your left-hand side, basically we just check what is the model and so on. So example 1 comes from Kunder's book. You have this book. It's the so-called Bible. It has the answers to everything, but you can never find them. The model is not exactly the same as in the book because we don't know equations they were using and how they implemented it, but it was our first or best try to get it together. So our goal is actually, we will analyze the behavior with AVR and with AVR and PSS. We will not do just the no control because that's just too simple, right? So at least you do the first example of power system dynamics with Modelica. Okay. Everybody knows what this is about, right? So everybody took dynamics class or not? No, but okay, so somebody hasn't, so I can explain. So this is the one that you study either at the, maybe you don't study this on the undergraduate, but for sure in the graduate courses, it's for the so-called transient stability and small signal stability. You know, I always do like this because those are made up names. Stability is everything. And, you know, they're just characterizing specific behavior in it. But you have a nonlinear system, everything is stability. It's just ways to classify it, right? If you didn't know, this actually is a very old knowledge. It came from the 1960s. There were some guys called Phillips and Heffron that started making these block diagram models of the generator. And then Concordia, Di Mello and Concordia were the first ones to use to explain the instability of interconnected systems. So when they started interconnecting systems for the first time, they started notice that, oh, for some reason they start oscillating against each other, and they found out that, oh, we have to actually change the gain that you have in the system, because otherwise it will make the system run wild. So yeah, that's that paper. And this is what we're trying to study with the model. So you didn't hear me talk about power flow because I don't do that. And I never want to do that as my research. Because then my poor students will never be able to write a journal paper. I am a great friend of Federico. He built this software called PSAT. So actually, the model that we're doing in Modelica is the same as implemented in PSAT. And you will see that the blocks that we're using are all the ones from PSAT. And the reason to do that with this tutorial is that you can reproduce the results. You can also generate a different power flow and try it out. So that's why we're using PSAT. So what we're doing, you don't need to install PSAT or anything. Everything's provided to you in the slides to do it from zero. But what we will do is use the power flow results because it's the same model. We have the same equations as PSAT. So we can compare. And we can you give you the simulation results so you can compare if you get one-to-one result as I offered in the seminar, right? Oh, I'm getting confused. It's this one. Okay. All right, so next slide. When you go in PSAT, if you want to redo this, you load that model called D/Kundor2MDL. You click on power flow, and you get all the solution. And notice here is the initial conditions for the state variables of the dynamics. So that's how we started figuring out how to do the initial guess, because we actually could see what was the value that they got in PSAT, and then, how do we get that value in our model? So you can look at that. And when you get this static report, basically what you need for initializing a dynamic model is the power flow, which is PQ, V, magnitude, V angle. So we're going to provide those into the model. You can do that by hand, but if you are lazy like me and my student Tim, but he was clever, I'm just lazy. But my student Tim built on my GitHub, you can find, or the GitHub of people that works together with me. This is a set of Python scripts that take PSSC files and give you Modelica records. Okay? A Modelica record is basically a record of information that you're going to use in the model. So you can put a list of parameters, whatever you want. So in this way, you can in Python have a power flow model in whatever you want and generate all the different initial conditions you want, and you don't have, you can pass it directly in a way that is easy to work with. So we won't use that today, but you just, if you end up using this tool for whatever reason, then you know what is available. Next one. So this is the summary of what you need. Voltage, magnitudes, and angles at each bus, P and Q through the system. All right, so this is our goal. You have seen it before, right? And you can open it in your screen under here. So this is our goal. Okay, so under working examples, or as I have done here, you create the sub-package called example 1. You already have it if you're on working examples, or under example 1, you create one called generator. So you go to a new Modelica class, and then you say generator, and then you choose what? A package. So a package will contain other things inside of it, right? All right, so now under example 1, we have generator, and that's what we have under there, you see? So we're trying to reproduce this exactly. All right, next slide. Now what we want to do is to create, that's what we just did. All right, this was a little bit more detailed. Now what we want to do is to assign this additional attribute. Okay, I made a mistake. Can anybody see what the mistake is? That you shouldn't have created the class. I have to fix that slide. Can you take a note? Slide 19 needs to be deleted. Yeah. All right, so we do like this. So this is nice that this happened, because now you get an emphasis on reuse. So what we're gonna do is that we're gonna actually go new Modelica class, and we're gonna use the option of create the name generator, and we're gonna extend a model. So you can define partial models that contain all common information between different models. In our library, for example, we have a model called base machine. Base machine has the 2 mechanical equations and all the parameters required for that. And all the machine models have the same, so we just share them across them. So you can, when you create a new model, you can extend for the base. So if you're familiar with object-oriented programming, basically we're inheriting all the attributes from that. So here we're going to inherit from interfaces, generator. So there we go, and we declare, we have a new model called, where did it go? So now you have here this generator. Yeah. So you have this model called generator that has inherited the attribute. To see what's inside there, you can go here and you see extends interfaces generator. So you don't need to redo all of that. You have it inherited, right? All right, so that was the point of that slide, to inherit that. Slide 19, I get rid of it. All right, now we drag and drop. So we go back to generator here, and what do we need? We're gonna use, as the synchronous machine, we're gonna use the order 6 from PSAT, that is under electrical, and then you go to machines, and then you go through PSAT, and then you go to order 6. And then you drag and drop. And it says, please choose a meaningful name. What name did I use here? I don't remember what name did I use, so I just call it order. It's a synchronous machine. I think it's not really relevant, so. All right, so there you have the synchronous machine. And the synchronous machine has inputs on the left-hand side, outputs on the right-hand side. And then you have some crazy things coming out of it on top and bottom. Those are values of the initial conditions. sometimes you need the initial conditions from, for example, the field voltage to be able to initialize the AVR or the automatic voltage regulator. So the way that we propagate this value is through an additional output. And this is just for graphical convenience. You can do it, you could do it in many ways, but we did this for graphical convenience. So now, double click on it and fill up the stuff. So one important thing that you should notice here is that you have a predefined value here in all of these things. These are all the start values that are pre-calculated within the model. So again, if you can go here and say open class, it will open another one here in the tab. And if you go here, you can see that we have our extents from the base class, right? So I told you about the base class. You have parameters, all fine. And here you see you have a start equal to EQ0. All right? So we're gonna start, the start value for that variable is pre-computed as EQ0. Where is that calculation? You go below and you find it, ID0, where is, here's ID0, IQ0. You remember what these things mean? If you don't know what this means, this is the direct axis voltage. So we take the synchronous machine and we model it in a 2-axis rotational frame. So the ED0 is on the direct axis and the EQ in the quadrature axis. And then you take square root of the square and then you get the voltage phasor. So anyway, here you see ED0, and as you see, we're pre-calculating that from parameters. So you get our value of ED0, EQ0 are pre-calculated, and those then are then used for the initialization process. That's how we get it to initialize the same way as PSAT and as PSSE, because we give it the best initial guess that we can, and so it gets as close as possible. And here you have this model has order 6. It means that it has 6 differential equations. So you can count here, 1, 2, 3, 4. What's the other 2? Anybody knows where's the other 2 differential equations?
Swing equation.
Yeah, where are they? They're not here. Base machine has the base equations that everybody shares. So you have to go to base classes, base machine, and then you go down, equation, and the 2 derivatives that you were missing. All right, so that gives you a feeling, I hope. All right, so we go back. You can, I don't know if you have parameterized it or not. I'm not gonna parameterize it, guys. I'm too lazy. But the point is that this is how you do it step by step from scratch.
It has the built-in initial values. I mean default values.
But those are not the ones for the example. Look.
Oh yeah.
It's intentionally left empty. So, all right. Has anybody parameterized it now or not? You don't want to do it? You're stuck somewhere?
Mm-hmm.
Are you good? No? Man, you guys don't like saying anything. I don't have any cookies to give you, so. Oh. So let's parameterize it. I'll make you do a few things by hand, at least get the basic thing working. You know when we are here? Nobody knows how long.
Until 3.
2, 3. Probably nobody has this room after that, right? I don't know. I mean, if you want to, I can also stop now. But it's up to you. You cannot do it.
Yeah, is it?
Because where are you trying to drop it to?
Is it long?
Okay, so open generator there. Where did you put this file?
Like it's in
Is it somewhere where you have write access or not? It doesn't let you, huh? Strange. Have you tried saving?
Yeah, I just saved it in the same folder.
Ah, right. So you know, this is the Mac, right? Oh, I made it. You have to do. I don't know. It's 1.9. That's why I told you don't use that one.
No, that's the one on the one on the slide. It's fine to mention.
I mean, I'm using 1.11.
I'll be back when you. I'll be back.
I'm using 1.11.
It works?
Yeah. So it's.
I didn't know about that error. So that is, if you write it down, I'll fix it for next time. I don't know what's going on.
Yeah,
Do you have a Windows? Tell me.
So please,
Wait, where's TQ double prime? Wait, where's
Yeah.
TQ double
Which
prime?
one? Here.
I don't see.
This. That's the icon.
No, TQ double prime.
And that next one. The next
Oh,
one.
there's
The gears is
Oh,
the
0.0 cell. Oh, the
You
second
see
one.
it right in there, right?
I'm not sure which has to be larger. I think
you should be mostly familiar.
What's up?
there are two TT double primes. I think the first one should be TQ double prime, right?
Yeah, because it's the smallest one. Another, but that one I can fix immediately, I think. You see, I've done this several times and nobody tells me the mistake. So
Which page is this?
we are now in page
So the only thing we need to change the machine.
21.
parameters, right?
Yeah, so this one is TQ double prime. Yeah, you just need to enter the data. It's just to do the exercise, you know. I know it's kind of boring, but all of these things that you're doing by clicking, you can just do it in text. When you get bored of, when you get used to it, you know. So that's the nice thing of being able to switch between screens, because then you just parameterize all
Yeah,
your
I
things.
like this switch. Like you get the code, you get the.
So normally, when you have a little experience, right? You want to set up a little system from scratch. You drag and drop everything, and then you look at the model that is already ready. Meaning that you look at. So, for example, you look once you have everything connected. Let's say like this. Then here you fill out all the parameters. That's the faster way of doing it, because you know where they go, but you gotta get to know a little bit the library to do that. All right, let me close a bunch of stuff here before I continue, because it's becoming a mess. All right, so let's go back. So somebody was asking me, here in the gears is the diagram view. This is the one that you use for editing. The icon view only changes the look. Okay, so for example, if you want to add here this, yeah, look, if I want to add like that, then you have it in the icon. Come on, stop it. I don't know how to stop it. All right, yeah. So now when you look at that thing, when you reuse it, you see the icon on the lower part, it has a line through it. So you can you can put a picture in it also if you want to. There's ways to do it. So if you want to make it look pretty, it's possible to do these things. Okay, so now we have the generator and it has parameters. So the next step is to add the power flow values, right? So in this example, you only need to fill in this part of the parameters in on top. Sorry, not on top. It says power flow data. Okay, that's the only one that you need to fill, and don't touch this one. System-based data. Don't touch that because that's going to be populated automatically from the upper layer. Because everybody in this model, everybody has the same base and everybody has the same frequency. So we're going to propagate that through all the blocks.
What was the?
Do you need me to go back?
No. So we just put variables, right? For the.
No, you leave. So if you see this,
I mean, instead of zero, we don't do anything.
look here.
No, I'm saying, do we need to?
Don't touch this too.
But in terms of we need to change.
Yeah, you need to provide those.
But where do we get that?
What is written there? V0.
Oh, okay. But it looks the same way. V0 is equal to V0.
Yeah.
Okay.
That's, you can call it Peter, for example. If you want to give it a name to the, no, it's just the.
So, I mean, the value of the parameter is exactly as the name of the parameter.
No, we're just using the same name. Maybe this is too confusing. But the thing is that
No, I understand the concept. It's just coincidence, right? But
so from the upper layer, so here we're going to add a layer on top, and then on the top layer, we're going to add all of the values. The reason is that normally in power systems, if you look at it, we will use the same generator model for a lot of stuff. It's the same exciter. So what we do is to create one single container or template that you just have to parameterize it. So we call it groups. So that's what we're trying to do here, so that you can reuse it if you wanted another generator.
So this is how.
Yeah, this is zero, just like that. Yeah. So that's what you need to fill in there. You get it? Yeah.
So, and this values we're getting from like a file we're going to add, right?
Yeah, in this case, we got them from PSAT.
Okay.
Yeah, so you can check that PSAT model if you have MATLAB to open, and you will see the same thing. Okay. If you
and type stays the same, angle is in degrees, right?
No, angle is in yeah, there. Oh, that's new. We added that. Must be Maxime.
Oh no, there is no option. You cannot change it.
Okay, so it has to be in degrees. Yeah, so that's important, because if you put radians there, you're gonna get the wrong answer, because we use those values, as I showed you, to pre-calculate the initial variables. So internally in that parameter calculation, we're doing the conversion to radians.
Because here, I mean, I checked, we cannot change any of them. So probably when we prepare the data, we need to make sure that they can correspond to this scale, megawatts and kilovolts. Yeah.
So when we started, we were doing everything in per unit, but now we're starting to add types. But then you need somebody that has experience with Modelica for a few years. So Maxime is doing that now, and then I will stop doing that for a while until somebody else gets experience. All right. So the next thing is to put the AVR in. The AVR, let's put it in. So you don't need to create any other package or anything, by the way. So in the solution is divided on how you do it one step, and then, but when you're doing it, you just go and add the AVR, right? So where is the AVR? Is in controls, excitation systems, probably, or no? Yeah, PSAT, excitation system, AVR. So which one is it? AVR type 3. Okay, so. Okay. All right, so now is where it makes sense to talk about how do you connect things, right? Not yet. You just parameterize it, and we don't have a stabilizer. So the stabilizer is absent. Then it means that you have a zero input. And to use the zero input, we will go to the Modelica blocks library, and we look for sources. and then you'll have a constant. All right, so once you have that, you can just go and connect it. And well, we didn't need to connect it, but what we need to do is to fill it this. Of course, if you wanted to be able to change these parameters of the AVR externally, then you will assign them a name if you want to do that, okay? But I will not do that right now because it's not, there is other ways of doing it. All right, so 0.0001, 0.015. Okay, that's it. And this one, it should have been called PSS off. I don't know how to do that. Constant value 0. And then where is rename? There's no rename. Screw it. It doesn't really matter for our purposes. So.
Attributes. Right click attributes.
Right click?
No, on the exciter. I want to change the name of exciter. Right click. No, right click on the exciter. Attributes.
What's this supposed to be called? No, but this is not the one. Okay, exciter.
AVR, I think it's called AVR.
Okay, here, this one, all right. Now I learned something new. Because I don't really use OpenModelica most of the time. I use the Dymola. So.
Well, what was the name? Or it doesn't matter. Yes, I saw.
It doesn't matter.
The name, yeah.
It doesn't matter. It's just to do a little bit. All right. So let's go to the next slide because if I finish, you probably did it faster than me because I'm an old person. Now we just have to connect all of the things together.
How to connect from the constant to VS?
So you look at here in the screen at the top. You see here, not in the screen, but behind me.
Okay.
You see that?
Oh, yeah.
That's to connect stuff. These are drawing stuff. This is the one to connect stuff. So when you want to connect stuff, click on that. Otherwise, you will have a headache.
Oh, okay, I got it. You need to click and connect for the second time.
Yeah.
Not the draw, but click.
So if you go from here to here, and then enter. Right, sorry. I forgot to do the second click. All right. And then VF output to the VF input. What happens with PM? PM is not 0. PM is not 0.
I mean, it's initial value from the power flow.
Yeah. So what do we do with the output of the input of the mechanical power of the synchronous machine? Well, we don't have one.
I mean, it's constant value.
But the constant value
from power flow
is no
output in the power flow. I mean,
from the initialization.
Yeah.
Okay. So from the power flow, you provide guess values, and then Modelica has to solve the initialization value. So the way that we do this propagation is by connecting the output here, PM0, to the input. And that's because we don't have a turbine governor. And now you're giving it the right value where the goddamn thing should start. Otherwise, it won't initialize correctly. Because you need, these are things that are very coupled together. So, all right, so I think we're all set. Oh yeah, we need to do something else. I don't remember. The voltage at the terminal, at the terminals of the generator. So that's an output of the generator that needs to go all the way here. So then we can move it up, Sorry. All right, it's connected, so I don't care if it looks pretty right
it
now.
goes where? From the V to...
From the V, yeah.
And goes to what? From V to V?
From V to V. So voltage terminals. So we don't have a sensor model in this case. Sometimes you need to model the sensor, right? Why don't we have the model of the sensor? Because it's included in the AVR model. So we're just connecting the input. All right, and then you have to connect the pin with the pin. And this is the most important connection. Actually, well, all of them are important. Nothing will work without it, but that's it. So now you have a whole model assembled of a generator plant that has an exciter. Okay, good. So when you look at the solution generator, that's the same thing. And this is what we have set up right now. So the next step is to do the network. So the way that we do it is in several steps, but you just need one subclass called network. So we go create new class. So new Modelica class network. All right, and just drop it there. All right, so now you should have one more called network there. That's it. And then what do we put in there? We put the name example1 for lack of creativity. So here we're gonna create a network model, so we can just call it model if you want to, or grid or whatever. So new Modelica class, I will call it grid. And that's all. All right. So this is very nice because it allows you to try to think how to be organized also when you're doing this stuff. Okay, next one. So now we get to use the generator plant that we just created by dragging and dropping it. So we call it G1. There we go. So you see, in the center of the icon, it says G1 now. Here. That's because on the icon view of the generator model that we built, we have the percentage name. So you can pass all of these things to the graphical part also. That's very useful. So you maintain consistency. All right. So here we have the grid, and we have dropped this guy in there. I thought I had done it already. Oh. All right, what did I do wrong? I'm trying. I'm doing something wrong, and I don't know what it is. I am exactly. Excellent point. All right, now we go fetch the buses. There's different buses here. There's this bus X. This is when you have 50 lines coming into a bus. It's just for graphical purposes, so that you can create 50 inputs, 50 outputs, and make the whole thing easy to wire up. So just use the standard one. And we should call it bus 1 or B1. All right, now we have B1. And then we do it again, drag and drop, B2. And then we do it again, drag and drop, B3. All right, there we go. We have everything set up. And then we have to add the system data model, which is under what? I think, I don't remember where that is in. Parameters, okay, so I think that's it under electrical system base. Yeah. And what, sys data, okay. So we added there, and you have this little box. And then we have to do something on the code, okay? So we go into the code, and on line 15 it said, or something like that. Where is it? Inner OpenIPSL. No, is it here? No, it's here. Here it is. It added it automatically. You can also add it by hand. I did that by hand when I did it the first time. Right now, I dragged and dropped, it just added it here, you see?
Yeah.
So you can do it by hand or drag and drop. When you do it by hand, you lose the graphical view. You lose the diagram and you lose the icon. That's the disadvantage of doing everything by hand. But
is there a way to write the code for the graphics?
It's here.
Okay.
Annotation, placement, visible. That's also standardized.
Okay.
That's why if I open it in the other Modelica tools, you get the same drawing. Sometimes it looks so, like somebody was dragging, like a cat was playing with it. Fucked up. All right. So then that's done. Let's go back to the icon view. Let's go to the next slide. We add the 2 winding transformer and a couple of lines. All right, so electrical, machines, controls. So you have branches somewhere. If you're faster than me, you tell me. Branches, PW line. There you go. And then we add 1 and 2 of them. You see that they look different from the slides because we have modified some of the original models. Now you can display stuff in front with this line. So it's just graphical things that we have added to it. All right, so you have the 2 lines, and to find the transformer, you go to transformers. Do you see it? No, so it must be on branches, and then PSAT, 2 winding transformer. Is that the right one? Yeah. And some of these things were really not fun to implement. You can ask, I think it was Hassan that did a lot of these things. He got to go do a PhD with Federico, so he's paid up from my side, I think. I want to do a PhD with Federico. All right, so we have everything there, and then we need to add the parameters. So do not edit SB because we will pass that. SN2220, PB400, BN400, FN, do not edit. And then we have KT, tap ratio 1, X 0.15, and R 0.
I have a quick question. So if we don't include any parameter, it's going to use the default one, right?
Yeah, but be careful because I'm not sure if everything has default values that make sense. All right, what's the next thing? The line 1. Where is the line parameter 0? X is, I should fix this. Can you tell me it's like 28 because this is just retarded. Why did I do that?
Fix what? All right, it's better not to see.
No, I'm trying, look at what I'm doing in the screen. I'm putting a multiplication there instead of just putting a value. That's kind of silly, you know, we should just do it.
But will it work if we use a multiplication symbol?
Yeah, for sure. Of course, I mean, the compiler will do that calculation for you, so.
But I mean, it's a good way to show that software.
Yeah.
You can put the expression instead of.
Exactly. That's what I'm trying to do here is I'm trying to teach you little things about Modelica at the same time that I teach you to use OpenModelica. So it's not that fluid, but because I have to explain you some things, but I think that's more useful than just going and clicking and so on. All right.
SB, it's better not to change because it's.
No, you don't change SB. That I have to fix also. So let me open the slides again. So you guys are actually being very useful for the project because now I found a bunch of things that shouldn't be here. All right. So SB should be called SB. So you should be left, do not edit, right?
No.
All right, let's go to the next slide. Everybody's good? And if not, you have the slides also, so you can just... All right, now we have the this thing called infinite bus that does not exist. So where is OpenModelica? It's here. So you go into buses and you will find there the infinite bus. And there's different types of infinite bus. You can take a look why they are different. They have different physical properties. This is the standard infinite bus, okay? So that's it. We don't need to parameterize anything there, I think. So what we need to do now, though, is to double click on G1. And now you see all of the parameters that we ignored and we attributed variables. Here you can modify them. And this is very useful in the case that you have 5 generators here and 5 transformers connected to a single bus bar. Then you do copy, paste, copy, paste, copy, paste, and parameterize all of them, and that's it. So it's to save time that we went through a little bit more of graphical modeling as we were doing, right? Okay, so on G1, we need to add this power flow data. Where is voltage? Magnitude 1. Power P and Q. Angle is 0.49. And then P is 1997.9999. That's 967. Now, when you are dealing with a large network, don't do this by hand. Just make a script that reads the power flow and populates it. Because when you're dealing with a large network, every decimal counts to that initial solution. It's very sensitive because of the way that it's solving for the initial case. All right, so I did that one. And then the infinite bus. So the infinite bus is absorbing all of this power generated by 0.90081. And now let me ask you a question. Do you think this voltage is acceptable? 0.9.
Within 10%, which is not acceptable.
Yeah, but so what do you think? Why do you think we have an initial condition like that? We're going to simulate an unstable system, and we're going to try to control it. So power flow will solve for systems that are dynamically unstable. Power flow gives you no guarantee on stability, absolutely no guarantee. Unless you do that full dynamic model, you have no way of saying if the system is stable or not. You can say some general things like, okay, most likely you're in good shape, but you have no guarantee. All right, then I gave you my preaching. And why do I have minus 1998? It's absorbing the power, right? So that's why.
I mean, also we have no power losses.
No. So it's all designed to be a textbook example, right? It's for, we have a very clear goal with this.
R is 0, right?
Now, there is some blocks in the library that allow you to introduce disturbances to the model. This is just because we do the same things as power system tools, so we needed something similar. So you can find that under electrical and events, I think. It's not events. Where is it then? Did it say there? Event, yeah, event. So because we have updated the library recently, so it must be under where? So it's not that.
No, events has it.
Do you see events? Can you tell me where it is? 1, 2, 3, or what?
Near facts.
There we go. Thank you. Sometimes it's hard to see where you are. So here, for example, you have this PQ fault, PW fault. The PQ fault is just a load change. So just to switch the load from one value to the other. PW fault is a 3-phase fault. And the breaker is just a breaker. You can just open it. And there's no more events going to be added than this. This is the basic that you need. Why? Because there is a way of modeling faults with the Modelica language that is way more meaningful. So that I don't have to redo that. There is a library for that. It's a very strict way. It's the way that I do it for aerospace. So I'm not going to invent. But here we do the typical power system fault. And you know how this is modeled, the faults, or you understand, right? Basically what you do is that at the bus that you're connecting an impedance. So this is really not what the fault really does, you know? This is a way of modeling it. So to model it, we add this x, which is 0.01 times 100 times 1230. And then we are going to apply the fault at 0.5, and we're going to remove the fault at 0.57. Now, the last step after we have done that is to connect everything together. You don't need to wait to connect everything. But before you connect it, look at something, right? Go to the, before you connect any element here, go to the view of the text. And if you go down, you have annotations, you have no connect equation. So what you have is only the class instantiations. You're saying we're gonna use, in this model, we're gonna use these classes. And now when we do this connection, it automatically creates those lines of code for us. And so on. So going back to this, now you see the two connections that I just made in the code. You see? So that's very flexible because you can reorganize the topology at any time you want just by redeclaring the connections in the way that are set. All right. Copy. Hey, I'm missing a line here. Yeah. You see, I've done this several times. I still make stupid mistakes. Did I delete the transformer? Jesus Christ. You see, don't become old. I don't know how you can do that, but I can't see well anymore. I deleted also a bus. I don't know why copy-paste doesn't work in OpenModelica, but that's the main reason I don't use it for all the time work. It does, it's just an OpenModelica thing, you know, it's an implementation. All right, let's go. So you see, all the buses are saying V, PU, and angle. Those will show the final value or the initialization value or whatever you need them to show. All right, I give up. This is taking too long and you're getting bored. So hopefully you have gotten further than me doing this thing. So now you have this.
And fault is possible. Right?
Yeah. Yeah. You can double check on the solution. PW fault. Yeah. So, all right, we're done with the modeling part. Now, we are going to first load the results from PSAT. So we go into the plotting side. What is this? Code. All right. So file, and then there should be something that says load open result files. So if you want to compare something, the useful thing is to have whatever you're comparing to measurements or whatever, you can load them on a CSV on this thing. So let's see, where is my OpenIPSL master? There we go. Application examples, tutorial, And then here you have the case without the PSS and with the PSS. So this is the dynamic simulation. And when you open this, you will have the simulation variables browser. I'm gonna try to, God, doesn't go into, there, almost. Come on, you can do it, there. So you just click and it will plot the, yeah. That's the field, that's the speed. That's the field voltage, the speed, and some other stuff. Yeah, that's field voltage. What you can see here already is that the thing is getting saturated. So that's the point of doing this, is just to load the variables so we can compare them afterwards. Now we can simulate, so we go back to the modeling window, we click on the simulation setup, and here you're pretty much, this is the fun part, let's say, because you can play with all these different integrators. So you can choose a fixed time step in solver, and I'm gonna choose the time step to be 0.001, and then I wanna use a Runkuta, where is Runkuta? Rungekuta. I'm gonna use a Runkuta. Yeah, that's fourth order. E to the -6. And then you have a bunch of options. And actually, OpenModelica is the only software that really allows you to play with the solver in this way. You have simulation flags. I should have some. I don't have my flags here set up. Well, I must have it in my settings of OpenModelica. With simulation flags, you can choose many other solvers and things like that are not in the GUI. Okay, you click OK. So you have set up the simulation and it's compiling now. So you see here, this is everything that it's doing that we discussed during the talk. And you can find all of these files under your working directory. So you see here is where actually the C code compiler is called, is GNU C compiler, GCC. And now it's executing the compiled model. I have these errors here because I'm using some special flags. So just ignore it. I think I can set up my working directory correctly, so I'm gonna have to redo this to show you, or find the directory that I put. I think it went into the multi-body intro because I was running that somehow. I think it went here. No, it didn't go here. Maybe I'm lucky and it went to my working directory. Yeah. So you see, now you can see all the code that has been generated. Okay, before I show you some cool things there, what we need to do is now you will have the results here in a mat file. And now we need to go look for the AVR. So that's under the generator. That's under the AVR. And that variable is the field voltage that we want to see, right? So where is the field voltage? I don't see it. Here, VF. You see? Look at the screen. It's red, right? Now it's blue. All right. That's why I chose the Rungakuta, because I know that I will get the same result that PSAT for this example. Now you could try another solver and you will see that you will not get the right answer. So that opens a question, right? Who's right?
I mean, I have a little bit different. Almost no.
Let me see.
I don't know.
I have a tiny bit of difference. You can relax there. If you go, now you can actually study what they show you in the dynamics courses, that the stability of the numerical simulators and all that stuff. So you can go and make the time constant of the AVR as small as your model time step, and that thing will not run. It will start oscillating. But that's not a system oscillation. That's a numerical problem. Okay? So it actually is quite fun, because then you actually start thinking how you should simulate things, so instead of just dragging and dropping the stuff. All right, so we compared, we did everything. You can look at all the other variables if you want to, but I know that we're out of time, but I would like to go through the OM notebook and how to linearize and simulate the model from OM notebook. If you want to stay, I do this and then I stop. Is it okay? All right. So as I was explaining you, OM notebook, so look at all of this fun stuff that you have here. This is all the C source code for your model. So actually some people takes this source code and runs it in any machine they want because they just have to recompile it with the GNU C compiler. That gives you a lot of opportunity that you cannot do with anything else. Now let me see if I can show you one more thing. I don't know which one was. There is a special flag that allows you to generate the graph, the connectivity graph of the system. So you can actually visualize entirely how all the equations are related to each other through this bipartite graph. Now that might not be so useful for some of you, but for some other people it might be it's good to understand how the equations depend with each other and so on. I think it's not going to, this is not the right one. So I think I say layout, organic. Okay. Yeah. So now you can actually see how the different equations are related to each other. That's really the network graph of the model. I know a lot of people is using this for the molecular dynamics. They want to understand how the molecules are interacting with each other. So that's how I found out about this feature. So for me, for example, it's very interesting when I click here and you see that this is the ED2 prime of the machine. So you can actually, if you have a large network, this is extremely useful to understand what are the critical buses that you have, what are the critical equations. So you can really exploit a lot of these things. So this is all with these special flags that you can use. You can use sparse solver and so on. Now, if somebody's interested, I'll let you know how to do that also afterwards. It's fun. I really liked it. I could never see the graph of a power system. Now I can do it. I think I have a bigger.
So what are the nodes? It's states or the buses?
It's the equations. So it tells you what is the dominant variables.
Okay.
Yeah. Yeah, it's a different way of looking at the thing, right? Buses are meaningless. It's state variables that matter. Yeah, and switches is death. All right, let me go now. So OM Notebook should have been installed when you install the OpenModelica environment, and it has the icon of a book. So I hate this. I don't know why they changed all of this stuff. So if anybody sees OM Notebook before I do,
you can search, right? There is search at the top right corner.
Yeah, but then it goes to stupid Bing. Who uses Bing?
No, it should search there.
There we go. All right, there we go. So you open OM Notebook, it will open Dr. Modelica. Dr. Modelica is a interactive class that you can use to learn the Modelica language. Okay, that's not what we want. We want to use example 1 ONB within our the files that I provided you. So it should be under your OpenIPSL master, application examples, tutorial, notebook tutorial example 1.ONB. All right. So at the top of this thing, we're gonna do a few things. First, we're gonna set the root path to where my stuff is. I don't know where your stuff is, so whatever this part of your directory is, change that to where the files are. Okay? So then you do Shift and Enter to evaluate this cell. This purple area is called a cell, just like in Mathematica. And you do Shift Enter and it should display you those results. Now, let me see where I am. Yeah, so we're right there. So you should go to ONB example 1 /ONB. It will pop up, give it your right directory, and we should be good. Now you evaluate with Shift Enter. So the first command over here is called load model. It will load Modelica. I'm loading the Modelica standard library. Next, the next command, load file, is loading the OpenIPSL. And the third one, I'm doing loading the example 1 package, the solution that we did. Okay, and then it's just done. If you didn't set the path correctly, you made a mistake. And then the next thing that I do is that I instantiate the model. So that means that the OpenModelica compiler is aware that I'm going to use that model. And I simulate. The simulate command is available in it's not part of the Modelica language. This is a command from OpenModelica environment. So the way to call it and so on is defined by the OpenModelica scripting API. So if you go to the internets, then here you go, OpenModelica scripting API. There is also a Python API, which is basically passing commands to it. So here in the scripting API, you will find all the commands that the scripting API is using. I will show you how to do 2 of them, which is simulate and linearize. You can also do, we will also do build model. So simulate is, you can even do dynamic optimization, optimal control. For free, huh? You don't have to pay license for this stuff. The thing is that you have to learn how to use it. It's not difficult. All right, where the hell is simulate? OPQRS. All right, R, S. All right, simulate. Here you go, simulate. So you see, simulate, all of the inputs that you can provide are here. So you can give it the class name, the start time. That means that you can start simulating. Let's say that you run a simulation at 50, and you want to start another simulation at 50 or at 25, you can start from 25. You can also linearize the model at 25. You can linearize the model at any point of time. Here you have the tolerance, the method that you will use, okay? And basically everything that you did through OMEdit, you can do through the scripting API. So OM Notebook is basically just a little notebook to write all your scripting commands before you make a script that just runs everything alone. So this is very useful, I think. I mean, for me, it's useful. Anyway, it had simulated already while I was talking all this stuff. And it says, no, it's not correct. I didn't run it. All right. So now it's evaluating the expression. And it should finish and give it. I don't know why I have the list here. You can use the list command to just look at what's inside the model in textual view. But it's running now. Hey, get out of my way. So it issued an error, which is not really an error, it's a warning, right? So it's saying that this one's is not, it's a fixed start value, that's fine. And then other things, that's fine. So this is the list that I ask. This is the model that we simulated if you want to check the parameters. So remember that I was multiplying some silly thing. Where was it? On the line, right? So where is it? Buses, branches, line. Look, still there. That's because you're doing that compile time. So it lifts it correctly. That's very useful. And here are the voltages that you plot. I plotted the infinite bus. The generator bus is bus 1. So that's the red one. Now, if you want to look at any other variable, you just go and look at what are your variables to plot. And you can plot anything you like. This is the field voltage. All right. Now, we have the model already there. To linearize it, we have no inputs and no outputs. So what should be the result of this model linearization? Any guess? Linear equations, correct. And what kind of matrices will be non-zero in those linear equations?
A matrix.
Okay. Because there's no inputs and no outputs. What we would get out of this, with no inputs and no outputs, is the stability matrix, right? So this is just what I showed you. There is lower in the bottom way of just doing all these simulations to see what value of the gain you should do. This is a manual way of doing the root locus stuff that they teach you in the classes, right? All right. Here you have the instantiate model and linearized model at time 0. Remember that if you linearize a model at time different than 0, you're going to get a different set of eigenvalues, especially if you do it when the model is saturated. Okay? So it gave us again the same warning. And then what happens? You generate a file. That's what it did. It generated a linear model. Let's go open it up. So linear, where is it? Do you see it? Linear, tutorial. Oh, I cannot see it here. When I do it in the Mac, I can see the file directly. Here is hiding it somewhere. Anyway, but if you try to open this linear model and you list it, that's why I use list here. You can see here x0. That's the initial x vector with all the initial states that you have, and then you have the A matrix. So the first element of the A matrix, second element, and so on. Which one is this one? Anybody know?
Speed.
You know everything, right? Why is it the speed?
I mean, because I take derivative of the swing equation, the first part to get.
And that is 2 times pi,
Yeah,
so that one is the multiple of pi. That's how you check that. Always check if you get a multiple of pi in one of these 8 matrices. Usually, if you don't get it, there might be something wrong. But if it's in the nonlinear state, then you will certainly not get everything the same. All right. And then what happened with the other matrices? They're not there, right? This is the linear model being assembled here for simulation. So you actually can use this model and do a linear simulation. Just exponential decay, basically.
But if the system is very large, it's going to generate very large text file.
Yeah. Yeah, but you shouldn't look at that file, it's too big. So what I did in this little piece of code is that I loaded the file and instantiated the linear model. Then
How do you know the indentation?
you get the names. Is the names that you have in each state has a name from,
Can you define that?
you decide. Well, I mean, the order of the states, you will know what they are. It will come in this list on the, which one is it? There is a file. I'm sorry, I don't remember right now. I'll try to remember, but there is a file that lists you all the states and their names, because if you looked at their models, all of the states had a name next to it. So then you know exactly which states they are. Now, to format the linearization output, in theory, you can go inside of the OpenModelica code and change it how that's been done. But then you have to learn how the back end works, the compiler. So I don't know much about that, to be honest. I do as much as I can, but I'm a professor, so I always have to spend my time doing stupid things. Writing grant applications. So what I do here is that I'm retrieving the A matrix, so you have a text file. It's a string in the text file. Okay. So I converted this string. I read it, and I do this command called get parameter value A. So it provides me all into that A string. Then I write a file where I define the string. So I write a file called evaluate A matrix.mos, and the file that I'm creating has this in it. It's just this single command. Is that A is equal to the string. It's like text to num or something like that in MATLAB. Num to text, text to nums.
Strings.
Yeah. So these are internal OpenModelica compiler commands that I'm using. So, and then you run the file that you just created, and then you get the eigenvalues and eigenvectors. This is because you're using the free tool, okay? I can show you right now how Modelica does full linear analysis and provides me a report. So it depends, you get it for free, then you have to do it yourself.
But
so,
the open
okay, just
the software we are using.
OpenModelica.
No. The
OpenIPSL.
Yes. So will it work with other Modelica tools?
Modelica, JModelica, and OpenModelica. I am still working on my free time to make it work with System Modeler, but it's their fault.
Well,
and I'm in contact with them because it's their compiler not initialized it correctly.
Well, what is the best commercial?
They all have their
plus and minus.
Yeah. So you have options.
I mean, you can try all and what you like for your particular task.
I really like System Modeler because it runs natively in the Mac. The only reason, plus it works with Mathematica, but I like to use JModelica, which has no interface.
Just command line.
Yeah, but JModelica is a complete suite based on Python, so I can use everything from Python. So you can use one to do the model editing, but when you want to run calculations, do whatever, once the model is set up, you move environment.
Oh, yeah.
And I use MATLAB Simulink for the calibration stuff. I can show you if you are interested. But let me finish the example so that if anybody wants to leave, they can leave. So here you have the A matrix that was read. Here you have the eigenvectors. And here's the eigenvalues. So we know the system is unstable. So which eigenvalue is the one that is unstable? It has a deposited real part here. Right? So I think you must be a little bit tired or frustrated, either depending on how your computer behaves. That's pretty much it for what I would like to do, because I think you guys have to do other things and so on. The next part of the tutorial is example 2, and it's basically implementing the PSS. If you have never seen a PSS, it's actually this one. I have one of those in my lab. It's a stupid box. You can only give it parameters. Okay? But that's how they look like. And this is also a very old problem. Is the year that I was born, they reported all the relevant results about PSSs. So you joined a very interesting and tough business where everything has been done before you. So why not do it differently? Maybe you find a better way of doing it. All right, so this goes through how to implement it. The OM notebook has the parametric sweep, so you can do this root locus. And then you can compare the eigenvalues from without PSS and with PSS. The last example is to work with the IEEE 9 bus system, so you can try to see how it works with a large system. Doing this by scratch is time consuming, so. Okay, whoever needs to leave, go ahead. I can take a lot of questions. the example one, here it is how you do everything with the command line, okay? All the linearization, everything. And here is how you do the linearized analysis with command line. In case you want to work with command line. I love working with command line. It's like, I hate GUIs. So that's why I try to share it, because most of the time you can't find anything. Now, you're asking me about the tools, right? So the most familiar I am is with DMOLA, just because it's the one that I started with, no other particular reason. It's the oldest one. Unfortunately, only works on their Windows and Red Hat operating system. So it does work with Fedora 23. I have it in my virtual machine. So it's.
But design-wise, it's so not good.
No. Well,
I mean, if it works,
it just looks kind of ugly, if you ask me, right? But everything looks ugly in engineering software. So I can load you the library here. You know, I have a little script that does everything for me. So let me do that, because I don't really want to keep you so long unless you want to be here. So you can, with OpenModelica also, you can make scripts that load all the stuff that you use and so on. So this is my script and the stuff that I'm working on right now. So I'm working on this multi-domain model. So I have these libraries here, and you can load everything you need, because there's a lot of libraries that are external that are not yours. So if you want to find some libraries for something, just go to Modelica impact under GitHub, write Modelica impact, and you will find the impact repository, or just go to, I think there is a website for impact. It's like a crawler for Modelica models. It was done by Dietmar, also this guy from Norway. He's actually a really nice guy. Yeah, so and this is a good website to have. It's Exogeny's website. It's Mike Tiller. He's a consultant. He has a great book called Modelica by Example. So if you go there, it's an interactive book. So you can, it's all online, and it gives you examples that you can run on your browser. So you can do circuits. It's really, really a lot of fun. I really love this stuff. So you can simulate the models in the browser, and you don't need to install anything. So if you're curious, this is the best Modelica book there is right now out there. So that's the one that I will use for the course in part of it also. But I have some notes of training materials that I built over the years. So I will use those, because basically I'm trying to teach my students. So I know what I want them to do, but it might not cover everything that you need. So here you can find that book. Anyhow, yeah, this file should load everything. God damn it, what is going on? Let's just run it. Ah, you see, I made another mistake. I forgot to do that. All right. These are called MOS scripts, but it doesn't really work the same in all of the tools. They have not really fully standardized that. So you have things that will not work in OpenModelica. Yeah, but the main reason is that I don't have license to give you of DMOLA, so we have to use OpenModelica. Anyway, yeah, so here you have the library, the tutorial. So if you look at the tutorial, you go to example 1, generator. In the tutorial, I'm including, if you want to do a MOS script on DMOLA on linearization, this is how you call it. And here I'm using external Modelica libraries called the Modelica Linear Systems 2. So I'm using state space and transfer function blocks. I didn't use that for the OpenModelica example. Here I'm doing it in another way, as you see.
In OpenModelica, it will work, right?
No.
No?
No.
So this just proprietary DMOLA?
No. It's the Modelica Linear Systems 2 library. It's an open library, but it's only supported in Demola for some reason. Now, system modelers told me that they might include it, but now they want people to use Mathematica for the control system design. MapleSim wants you to use Maple for the control system design, right? So everybody wants to lock you into their tools, right? But that's, you know, unless somebody gives money to the open source Modelica consortium. So if you like doing that, you can do all the support for it, but then you have to do the implementation for OpenModelica. So that's kind of like the beauty of the thing. I really think it's an advantage rather than a disadvantage, because if a vendor puts the effort to support libraries, they have a better product, and you know, then they should sell the licenses instead of, you know, this is the one thing you can use because your model is in this thing. And in Demola, you can use this full linear analysis, and it will just run everything. So execute and close, and then you start doing everything, and it will give you a report. So you will see soon the.
And also at the beginning of presentation, the Kundor example, it was unstable.
Yeah.
So is it like numerical instability?
No, it's by design, right? Because we want to stabilize that system. So you just need to reduce the AVR of the gains of the AVRs. It's designed like that, so that you can. That's the idea. I mean, I don't want you to get a stable example. What's the point of dynamics if you get a stable example? So here you have a plot of the whole eigenvalues of the whole system. But this is, as I told you, this is the Modelica Linear Systems library. So how do I rescale that? Yeah. So here is that nasty mode. Here, you see? That's the nasty mode that we have. In the tutorial, you can see, yeah, here is the report. So you can go and look at the report. Always set your working directory. Otherwise, files end up in the middle of the moon. Well, it's an HTML file.
But the default is inside the Modelica.
No, you declare your working directory.
Oh, it's different.
You have to set it up. I didn't teach that. Maybe you should add to the notes that I should add to. All right. Anyway, here's my system report. And there you see everything, right? So remember, we have zeros in B, in C, in D. And here's the list that you were asking me. It's somewhere when you linearize a model, you get this list of states. So you have the index here and the name. The A matrix, these are empty. And it gives you analysis of the eigenvalues, contribution analysis. You get also the eigenvector analysis and the correlation, knowing what you do. So this is typical. It's not exactly with these participation factors, because that's only power system people do that. But you can code it up. You can actually open that Modelica Linear Systems 2 library. There is in the tutorial, if you have a Demola license or some, I know that there's one in UTK. This root locus will actually run the root locus for the AVR gain. So if I do call function execute, I have already configured that example just to give you the root locus of R in the gain. So you see it's doing everything here right now. All right, so now you see a mess there, but the mess is because you get all those eigenvalues moving into the right. Pretty cool. So very, very flexible. The Modelica Linear Systems 2 is extremely powerful. So imagine how I just took the linear model, linearized it. Modelica Linear System 2 has blocks that you provide. You tell, like we did, where is this model? So you instantiate a model of the Kalman filter, and for the Kalman filter function, you don't have to implement anything. So Modelica Linear Systems 2 is very powerful. It's been developed by the German Space Agency. So they use this for the space aircraft design. So you can look here inside of utilities, I think. No. Examples, yeah. So here you have different ways of using state space models, and these are the analysis functions. So if you open this one, you can look into the code, and this is telling you what they're doing here. It's another function, so you have to keep digging. All right, is there any more questions? Yeah?
Did you say that you did integration with MATLAB?
Yeah, I can show you that example.
That'll be very helpful, especially for control development, since there's not a lot of stuff where LQR and MPC.
Yeah, and that's why I have this toolbox that you will see. The toolbox is open source, but you require a license for FMI toolbox for MATLAB Simulink. If you have Demola, you don't need that, because the Demola comes with something called the FMI kit. All right, so then you already should have the FMI kit under the installation directory, and with that, so then that one will just import your FMU. But Demola's FMUs are extremely unstable and leaky. So you should generate your FMU with OpenModelica or JModelica. Those are more stable. If you want to see, this is the tool that it's called Rapid. I will run the GUI, but you don't need a GUI, because it was all developed without the GUI. The GUI was the last thing to do.
Well, it's really
No. So the way it works is that you have your Modelica model, and then you want to simulate it somewhere else. So you can simulate it in other Modelica tools, as I have just shown you. But MATLAB doesn't use Modelica, right? So what you can do is that there is this library called the FMI toolbox for MATLAB Simulink. So that allows you to use the same Modelica model exported in the FMI standard inside of MATLAB Simulink. And you can use it only in MATLAB, just by scripting, or MATLAB Simulink graphically. So my example here is the same power plant from Bosnia and Herzegovina. It's part of the library, so you have the FMU. It's not in the OpenIPSL yet, but I will put it. I was just cleaning it up. I can open it up for you here, so you see the whole chain of so let me see. I think I have a folder called Modelica. Okay, I know where it is. Do not fear. So where is this tool? No, I just, yeah. You know, if you don't want to have these problems, you have to learn to use Git better than me. Where is my Git folder? Recent places. All right, this is proving extremely unsuccessful. Here we go. No. GitHub prep. All right, so here, this is what I'm trying to clean up to upload. So there is this paper you can get online. If you go to GitHub and type Rapid, or where is it? Also, yeah. No, that's the wrong one. All right. So here you will get all the source code for this. You can do it for doing automated controller design, because what I give the software here is a reference. So you can give it the reference of a damned second order system, and you can calibrate the parameters to give you that response. That's what you can do with this tool. And because it's in Modelica, this automated parameter calibration tool is not for power system only. You can do anything. You can use it for your models, actually. So there is some videos there that you can see how it works. The paper is here. I'm just trying to look for the paper so that I find a picture that explains. This is what perhaps a bigger effort that we have done, bigger than the library, actually, because it's okay. So here you go. So Rapid, what it does is that you provide the model in an FMU, and the FMI toolbox is just working as a container that allows us to run the model in Simulink with Simulink solvers or in MATLAB with MATLAB solvers. And around that, we have optimization routines. So you can use whatever optimization routine you want as long as it has a link to MATLAB. So this was built to do parameter estimation or feature estimation. So you can estimate eigenvalues of the system just given a trace. So we will run the model, obtain the simulation, and after the simulation, you compare with the measurements. And that's basically it. So the model is this one. If you look on the internet, search for Mostar, you will find the place in Bosnia-Herzegovina where this comes from. And the reason I have this model, and you have the model and the measurements also available. So the reason we have this is because the father of the student was commissioning the AVR for that thing. And that's how I got it. Otherwise, I wouldn't be able to get anything. But so here is the AVR, and the AVR is the one that we want to estimate parameters for. So you're familiar now how we propagate parameters and so on. So this is how we have done it. This is the one that I showed you in the picture. Remember, of the PSS? That's actually an excitation system also. So it's that exact model. It's excitation system, static excitation system. Anyway, this is the one that we are. So when you are in the tool, if you go to simulation, and in OpenModelica, you don't need to do that. You directly go to export. But here, sorry. Where is it? Here. So this is the translation button. So you can actually click on FMU. And then you can export the FMU with different options. The option is model exchange only. So there you will exchange only the equations. Co-simulation using CVOL means that instead of exchanging the equations, you exchange the whole integrated model, like the power system tool entirely, let's say. Model exchange and co-simulation provides you both instances of the above. So it's just in a different folder inside of the FMU. The FMU is just a zip file with an XML file and all these other libraries. And then for the architecture that you have and so on. So this is the one that you export and then you import into the FMI toolbox. So I have already, in these demo examples that are reported in the paper, we already have some FMUs prepared and some examples prepared. We call them containers.
So the directive is written in Modelica. But
No, Rapid is an entirely MATLAB-based toolbox, but we run the Modelica models inside of MATLAB.
Got it.
Yeah. So if I go here, I don't remember where this is. Dropbox, GitHub, Rapid, Run Rapid. Okay. I should move that to the correct place. What was the next point in the... Let me just, I need to, you see, I really hate this command line. You don't have these problems. Always clicking here and there. I need this, the folder where this thing is. How do I copy the, I don't know how to copy this thing. All right, so let me see. Sorry, this is taking more time. I was not prepared to give a demo of this one, so I apologize if it's taking too long. Okay, Mac, Dropbox, MATLAB. All right, now I know where it is. Rapid GitHub, and then Rapid examples. And then, so, all right. So for example, one of the examples that you can run is the Cower low pass filter that is part of the Modelica electrical analog. And you can try to calibrate the parameters of the filter, for example. That's just, we did all of these ones just for fun when we were trying to get the thing published. And you can see that the journal that I publish is not IEEE, because this is impossible to publish IEEE because they are terrible people. So the journal that I'm publishing is called Software X. It's an open source software journal. So if you don't release the code open source, you can't publish there. So it's really nice because then everybody gets the stuff. Anyway, we were running this thing, and then I need to get the container, so load the container. And there we are. So here I have pre-set up the example, and then you have this Simulink model in it, as you see. I will load, where is it? Simulink, show Simulink model. So this model has been already pre-configured for this experiment, right? If you had to start from scratch, it will be a little different because you have to set up everything, the whole experiment. Where did it go? Yeah, poor computer is really giving up right now. Let me close these things. You don't need them anymore. Let's see how it's going. Because all right, give me my mouse, computer. All right, there's a simulation model. So here we have the block is called FMU-ME. Why is it called like that? Because if you go here and you go and look under Simulink, where is Simulink here? Simulink library. You're gonna now, this is the FMI toolbox for MATLAB Simulink. Now that requires a license. It's a company called Modelica that built it. But you don't need the license for the rest of the stuff that I will show you. So FMI, so here you have two blocks. Depending on how you exported the model, you have model exchange or co-simulation. So you drag and drop and then you build a model like this. I can do it right now, but I haven't generated FMU from scratch, but oh, never mind, I can do it quickly. So for FMU for model exchange, you drop it there, and then you need to populate it with a FMU. So you load it, and there's an FMU here already. I'm not tricking you, it's the same model. Huh? So no wonder, so that's it. That's all you have to do to work with your Modelica model in MATLAB Simulink. You just need this toolbox. And guess what? You can have linearization of the model. Everything that you do with MATLAB Simulink, you can do it on that. So, okay, so now the interesting things is here on the top. So if your model has outputs that you want to monitor, you have to declare them, right? So let me throw away this thing and just illustrate with the one that is prepared. So here, the measurements that we have from that power plant were active power, reactive power, field voltage, and terminal voltage. And here is the measured data. The only reason to have this block here and those there is for visualization purposes. You could just run this without all of that, but you know, you have to show something to the people that gives the money for the funding. So, and I didn't want to make a GUI, so this was the easiest way to make it instead of making a display and all this nonsense. All right, so I'm opening all the scopes. So here you have the terminal voltage. So remember that I am trying to calibrate the parameters of what was that thing? Excitation system. So in the rapid main window that you have here, you can choose what ODE to use. So that's the FMU that we're using. That's where the measurement data is. That's how the data is structured. You can also have input data. So if you measure the input and the output to something, you can declare it there. And here's the parameters that we want to calibrate. These are the model parameters. And here you have the time step that you want to use, the maximum number of iterations, the simulation time, the solver, or the E45. Okay. And here you have the simulink settings. You can choose an optimization algorithm here. So this is an external one called K-Nitro. It's a commercial library for optimization. I don't have it anymore, but in the project, we had to put it in. This is FMinCon from MATLAB. Everybody.
What is the best algorithm for this? In terms of
there's nothing that is better than the other. It depends on your use case. So when
no, I mean in this particular system, or
we had no information on the parameters of the AVR. So in that case, when you don't have a guess of the parameters, a heuristic algorithm at least allows you to find some good parameters to set. So people often argue about optimization methods, especially in power systems. Oh my God, they are horrible. The heuristic people hates the other people. It's nonsense. You use the thing that works. Let the mathematicians take care of the optimization, okay? So in this example, we didn't know, but if you have a good guess, you can use a conjugate gradient. And if you want to use both of them, you just configure them to be used. That is combi here. Our combi algorithm starts with particle swarm, and when you have reached a good local, you switch it to gradient. Why not? And that's what this toolbox likes to do. It's agnostic on simulation method, solver, and so on, but you do need to have an FMU because otherwise you can't run the model. Anyway, once you're done doing all this stuff, you click on Run Optimization, and what is happening here in front of your eyes is that a different set of parameters is set, and the simulations are being carried out. An objective function is calculated between the blue trace and the red trace. And because we're using particle swarm, the particle swarm algorithm, nobody knows how to explain how it works. It's very easy. In a conjugate gradient algorithm, you start going to the minimum. You don't know if that's the correct minimum. So the particle swarm, what it does is, as you're going to the minimum, it takes the parameters, it sets it off. So in case you had another minimum here, it will go there.
one of the parameters.
No, all of them.
All of them.
Yeah. That's how we have configured it. It was Azure that implemented it. There is a particle filter method there that is Tatiana's work. So you can add routines into it depending on your need. It's all like plugging stuff. So yeah. So we're getting close, but it all depends on how you evaluate your criteria, right? So you can say that I want the very, very, very tiny error, then it has to run a lot to can reduce it. But if you're not so strict, you don't need to do that.
But it's not showing every iteration. It shows like maybe one or every.
It's not showing you the iterations, no. It's showing you the simulations. So inside of every simulation, we're running an optimization problem. So you here have seen maybe 10, 15 optimization problems. So it's a work, it's what we call it. If you work with software, people call this a workflow. So in our workflow, simulation is one part of it. It doesn't mean that you need to do this way. This is just very simple when you're doing offline analysis and you have some idea of what you're doing. But I mean, you can do, if you do it by time step instead of doing, this is what Rapid does. But if you have your FMU and you want to simulate each time step and correct the trajectory, you can do that. And that's called dynamic optimization or optimal control, or what is it called now? Model predictive control. Model predictive control uses optimal control. Right? So people like to call it different names. It's all dynamic optimization, really. I think. They started doing that for missiles, you know? Computers were invented to make missiles be accurate. Now we use it for cats. and other things that I'm not allowed to say because I'm supposed to be a professor. All right. You have any other questions or something that I can?
So if I want to use this tool, all I need is to, I don't have that model and license, but I do have that, so I just use that export tool.
So you can look, I can show everybody so that if they're curious. Let me, so I didn't select the configuration here is not made to stop, it's made to run while I talk. So it will run there for an hour or so. It's made on purpose, right? So let me kill this thing. We need to add a kill button to this thing also because, I mean, ideally you don't want it to stop until it finds the thing. You leave it there and that's it. You know? All right, there I killed it. The same thing that I'm doing here, you can do it in Python. So if you want to do control design with Python, you might as well use the Python control libraries and the PyFMI. The PyFMI is basically a Python library that lets you run the FMU. It's included in Modelica. So Modelica is for dynamic optimization and model predictive control. But anyway, you were asking me about that kit. I think you can go under C program files. Say this is Daimola 2018 documentation, I think, and then you can look for. Do you see FMI toolkit there? Okay, so it's not there. Then go into M files. Yeah, FMI kit for Simulink. So that's their own version of the FMI toolbox from Modelon.
But it only works with
This is so the Dassault is a huge, immense company. If it flies, swims, or runs, Dassault has had something to do with it. And if you ask the ANSYS guys, it's the same thing, right? So this is provided by them for their users of Daimola. It's included in Daimola. Daimola has had a very, very long tradition with the control system community in Europe because it was initially developed in Sweden. Still developed in Sweden, actually. But it's been bought by Dassault. It's a French company. So it's the same principle here, but I don't know about them. We have used it only to test running FMUs for this multi-domain simulation that I talked about today. And it worked for that, but there's problems with initialization. I can show you that result if it's of any interest, or we can discuss offline so people can go and do something more interesting than listening to me. So, I mean, that's all for me. We can talk offline.
Thank you.
Done? So how many of you got to run the model, actually? One? But at least the example one, did you try running the example one? Okay.